hear me? You can all hear me?
Here?
Yes.
Yes.
So any questions from the last time? So last time we looked at some representations with the weights, highest weights being small numbers, involving small numbers, right? As you can easily see that as you go to higher and higher numbers, W1 and W2, then it becomes more and more complicated, right? But the procedure is this, the logic is this. Of course, for big representation, it becomes very complicated, but the main logic is that. Generally speaking, I mean, we saw also that if you have, at some point, there are two different ways to reach some point, then you can in principle have two linearly independent vectors, right? Actually, generically, that's what happens. In very special cases, they are not linearly independent. Okay? So the multiplicities can become quite large if you start from a very high weight, then N1, W1 and W2, suppose, are very big numbers, right? So then by the time you start tracking up all these points, the multiplicities will keep increasing. So it becomes quite cumbersome, to do that. Yeah, I mean, generically speaking, you can try to the chalks. No chalks here. Huh. There's no chalk. I should come back with some chalks. I have to take this. See, there's no chalk. What I was saying was that, I mean, in general, if I start from some highest weight, W1, W2, some highest weight, and then if I look at, say both are non-zero, if I look at I think I was calling x minus alpha 1, and here x minus alpha 2, you will get some points here. So this will be W1 minus 2, W2 plus 1, and here it would be other way around, W2 minus 2, W1 plus 1. And now I apply x minus alpha 2 and x minus alpha 1. So here I will get W1 minus 1, W2 minus 1. Both ways, right? So you can try to check, again, the way I try to look at the linear independence of these two states. You can check that, and you will see that both, I mean, it will be linearly independent if W1 and W2 are both not zero. If one of them is zero, what happens is that, so suppose W2 is zero, then this line doesn't exist, right? Because if it is zero, nothing can happen. It's a singlet of this SU2. So this guy is there, so they're not there, so there's only one way here. You can try to prove that, just from linear independence. So generically it will be increasing. The numbers will keep increasing. In fact, the general picture is that, for example, in 2-1, I think it was like, what was it? So here there was this, and then here, Q1, and then you had something like that, right? So here it was going like this, here it was going like that. Was it this, or there was more? Oh, sorry, there's one more point here. No, sorry, there's no point here. Yeah. So this is 4, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and there are multiplicity 2 here. That was 10 dimension. But now suppose that I had started with a bigger one, no? Then you'll have, I mean, if I started with a bigger value, let's say 3, 1. 3, 1, for example, then in this row, the top row, they spin 3 half, so it will come like this here, and then here there is, goes like that, here it goes like that, here it goes like that. So you see here is 3, 1, so this will become 4 minus 1, right? So 4 means spin 2, so there will be 5 steps here, I mean 4 steps here. Okay. Now you will see that here the multiplicity is 1, here there is 2, I think if I wanted to check it, but I think it is 3 here, 2, 1. So the number keeps increasing. I wanted to check that, but I think it's correct. So yeah, that is a difficult exercise to keep track of. Okay, so now let me just talk about something slightly different. I mean, not. I will come back to this. So we said that in general, the weight space, the weights are in general. So if I denote by W1 and W2, this will be integers, right? Of course, I'm not talking about only the highest weight, all the weights. Because we said highest weight is anyway integers, but then when we apply x minus alpha 1 or x minus alpha 2, they're again shifted by integers, right? So it's always going to be integers. So all the weights will be integers. These are all integers. But it turns out that these different weights can split into 3 classes. Just like for the SU2 case, this was SU3. For SU2 case, we saw that you had, okay, there we were talking about sigma 3 by 2, right? But suppose I was talking about sigma 3, then it will be all integers, right? I mean, for the sigma 3 by 2, you had half integers or integers. So for sigma 3, it will be all integers, but some of them will be odd and some of them will be even, right? So the odd ones, this correspond to, so let's say there's only one weight, W1. There is no W1 and W2, there is only one. These weights can be either, so they're all integers, but there will be odd and some of them will be even, right? So this will correspond, these are the half integer spins. half integer space. In our old language, these were half integer spins, and these were integer spins. Okay, but they split into two different classes: the odd ones and the even ones. When we considered the center of SU2, you remember that the center of the SU2 was a Z2, right? So the Z2, if you look at this, the element, so there was SU2, the full group now. Now I'm talking about the group, not the Lie algebra, the full group. Okay. So there was one element which was the identity. So this is a 2 by 2 identity matrix. So I mean this is contained in that, and also there was a minus identity. Right? Why? Because this is a 2 by 2 matrix with a, I mean, what is the SU2 is a 2 by 2 unitary matrix with determinant equal to 1, right? The determinant, so of course, identity is unitary, of course, but also determinant of this is 1 and that's also 1. That's because it's a 2 by 2 matrix, right? I mean, what is this? This is nothing else but minus 1, 0, 0, minus 1. Take the determinant, it becomes plus 1, right? So there are both of them, and since they are proportional to identity, they commute with every element of the group. So if G belongs to SU2, arbitrary element, then identity times, I mean, so let me call it, so what shall I, okay, let's leave it as it is. Identity times G is equal to G times identity. So it commutes, right? As well as minus identity times G is also equal to G times minus identity. So both of these elements commute with every element of G. That is why it's called the center of the group. Okay? It just commutes completely. So in this case, the center of the group, so this is now a 2-element group, a subgroup of SU2, and this is called center of SU2. Okay? The center of any group is defined as the subgroup which commutes with every element of the original group. That's the definition. So in this case, its center is just 2 elements, and this actually is nothing else but Z2 group. Why? Because this is, of course, the identity of this subgroup, and minus identity is another element, but square of this is again identity, right? That is a property of Z2, right? So this is therefore Z2 group. And with respect to this, we saw that if you look at this minus identity, when it acts on, I mean, this is of course in 2 by 2 representation. Okay? We have to now consider this in a given representation, in any of these representations. No? And we found, I think this, if you remember that, it was a very brief discussion I made, that when you look at this, so in that representation, I mean, I don't know, let's call this omega. Okay? This is the identity, and this is omega. Then if you look at the representation R omega, in whatever these weights are in some representation, if you look at the action of omega in that representation on these weights, you find that this acts as minus 1 on this and with a plus 1 on these even integers. I don't know if you remember that. It was a brief discussion I made before I went to SU3. Okay, anyway, we will see that again here. I mean, the way to do this is that, after all, this minus identity, I can write it as e to the power of 2 pi I, or pi I sigma 3. Right? Right? This minus I, because in general, remember, e to the I theta sigma 3 is nothing else but e to the I theta, e to the minus I theta. 0, 0. Okay, well, sigma 3 is simply 1 minus 1, right? Sigma 3 is just 1 minus 1. So when you take e to the I theta, it will be times sigma 3, it will just become e to the I theta, e to the minus I theta. This you can prove that just by, for example, expanding the exponential and collect all the terms, you'll find this thing. But so therefore, but now take theta equal to pi. So take theta equal to pi here. Okay, this is this element, theta equal to pi. because you can see that theta equal to pi, this becomes -1 and that becomes -1, which is that element. So theta equal to pi, this at theta equal to pi, this element is nothing else but omega, what I'm calling omega. So now we know how to act, because what is R omega? R omega is nothing else but R e to the power of I theta sigma 3, e to the I pi sigma 3. Okay. And we know how it acts. So remember sigma 3 in this representation will be half-half. Sigma 3 in this representation will be 1 and -1, say half the fundamental representation, so it acts as -1. But if you take integer spins, then this will be simply +1. Is that clear? Yeah, so let's see. So we said here the eigenvalues of sigma 3 are integers, right? Odd integers here. I mean, sigma 3 by 2 was half integers. So here I'm writing the eigenvalues of sigma 3. Eigenvalues with respect to sigma 3. So we said that there are this odd values of sigma 3 or even values of sigma 3, right? So now look at here, when it acts, the sigma 3 is simply odd number, right? I mean R of sigma 3, this is nothing else but e to the power of I pi R sigma 3. Sigma 3 is all diagonal, so we don't have to worry about it. So R sigma 3 is odd for this class of representations, because the weights are all odd. So whatever it is, look at any state, action on any state, sigma 3, eigenvalue of sigma 3 is odd. So it is e to the I pi times an odd number. So therefore it's -1. Right? Whereas in this class of weights, the sigma 3 eigenvalue is even. So the R sigma 3 is even in any state here. Okay? And so e to the I pi times even number, which is 1. So there's a distinction between these two classes. And that distinction is coming because of the way this center of the group acts on these states. That is so for example, what is the consequence of this? One consequence is this, that if I take tensor products of these different representations, okay? Tensor products of these different representations, say several of them, so R1 times R2 times R3, whatever. Whatever numbers, Rn, let's say. So different representations. Some of them may be odd. For some of them it may be odd. For some other of them they may be even. Okay. So I take the tensor products of them. But now let us ask, what is this? Which class? I mean, the final thing. This will decompose into direct sums of various representations, right? Some, I don't know, R1 prime. R2 prime, and so on, or M prime. So when you take this tensor product of representations, I can always decompose in terms of irreducible representations, direct sums of them. But if you look at now the action of this guy, R omega on that, right? So omega will act on R omega will act on each of them, right, simultaneously, because now we are talking about the group, not the infinitesimal generator, right? When the group G belonging to the SU2 or any group acts on this, it acts simultaneously on all of them, right? You remember that or not? It's so if I have some state here, I take so arbitrary element here will be some state psi 1, let's say, in this times psi 2, and so on and so forth, right? So question now is, how does G act on this state? Group element, not the Lie algebra element, group element. The way it acts is this state goes, G is applying on each state simultaneously, right? So this one, how shall I say, this goes under G, it will go to R1, G, psi 1 times R2, G, psi 2, etc. Rn G psi. It's from here how we deduce the infinitesimal generators. I mean, at the level of Lie algebra, it became the sums of terms, right? Because when you look at G infinitesimally close to identity, you write G as 1 plus identity plus, say, T, where T belongs to the Lie algebra, epsilon times T. And you substitute that, then you see you get one identity, everything identity, and order epsilon term will be sums of terms, right? Is that clear? I mean, R1 of G will be same as R1 of I, identity, which is one, which is nothing, which is identity itself, and R1 of epsilon T, epsilon times R1 of T. So the identity terms, so this term is identity, of course, identity in that representation. So everything, you just substitute that, and you look at the order epsilon term. Order epsilon term will come, for example, if I take this epsilon from here and identity from everything else, or epsilon from here and identity from everything else, right? So there it will be sum of terms, where there is a T acting on each one of them separately, no? There's a sum. But at the level of group, it just means that you are simultaneously transforming all of them at the level of finite group element, not the infinitesimal, but the finite group element. Okay. So now I apply the special case R1 of omega. I mean, now take the G to be the center of the group, omega. Then you see R1 of omega, R2 of omega, etc., etc. So then you see R1 of omega is either +1 or -1, right? So it will just count each of them. You take the product of them, right? So R1, some of them could be plus sign, some of them could be minus sign, depending on whether these representations are coming from the even weight or odd weight. So it's multiplicative, right? So what it means is that so now let's specialize to this case. So suppose in this situation, I have, some of them may be half integer spins, some of them may be integer spins, right? These representations. Okay, so now suppose odd number of them are half integer spins. Right? Odd number of them are half integer spins. Then when I look at action of omega, you'll have odd number of minus signs. Right? So the total eigenvalue of this will be -1. The action of omega on this state will be -1 if odd number of representations are half integer spins. Right? That means on this side, it can only be half integer spins, because now here's a direct sum, right? So the G is acting here. It's not a product now; it's the direct sum, because when I decompose in terms of irreducible representation, these are all, So you have each of them. So what is the conclusion? If there are odd number of half integer spins here, odd number of representations of reps carry half integer spins, then on the right hand side, every single term, R1 prime, R2 prime, Rn prime, they are all half integer spins. Okay. On the other hand, if there are even opposite, if you take, suppose there are even number of half integer spins here, then each one of them will carry integer spins. So this gives you some selection rule. But of course you knew that. I mean, after all, when you take the tensor products, the weights just add up. Right? I mean, it's trivially true, because weights just add up. Right? In this state, if you look at any given state, suppose this has some weight, this has some weight, this has some weight, then the total weight will be just the sum of these weights. So if there are odd number of half integer weights, I mean, when I say half integer here, I'm looking at sigma 3 by 2 eigenvalues. No? So if I look at odd number of half integer spins, then when you add them up, it will be a half integer always. So every state in here will carry a half integer spin. I mean, no? Half integer, the eigenvalue is sigma 3 by 2. So the decomposition will be half integer spins. Okay, so this was the situation with SU2. Now what about SU3? So I said here it splits into 3 classes. Right? Now let us see what, we do the same thing for SU3. So SU3 now, so we have a 3 by 3 matrix. This is a 3 by 3 matrix. And then, so what can be, I mean SU3, again we are looking for the center of the SU3, which means the elements which commute with every element of SU3. So therefore that element must be proportional to identity. Otherwise, because SU3 is all in general non-diagonal matrix, right? So the only possibility is that this is proportional to identity. Whatever it is going to be proportional to identity. Okay? But on the other hand, we have determinant equal to 1 condition. Now these are 3 by 3 matrices. Okay? So if I write omega times identity, this is nothing else but omega, omega, omega. 0, 0, 0, 0, 0, 0. Right? Now what is the determinant? It's omega cube. Right? So we are saying if it will belong to SU3 provided omega cube is 1. Right? Because determinant of this matrix is omega cube. Let's take the product, and we are demanding, because we are talking about SU3, not U3. We're talking about SU3. So determinant has to be 1. So that means omega must satisfy this condition. So that means omega is a third root of unity. Right? So this implies that omega is e to the power of 2 pi I times any, so plus or minus 2 pi I over 3. Of course, you could have also just 1, but that 1 has already been included here. Okay. There are 3 solutions of this. Omega equal to 1, omega equal to plus e to the 2 pi I over 3, or omega equal to e to the minus 2 pi I over 3. Okay. So 1 has already been taken into account here, and then there are 2 others. So there is a e to the 2 pi I over 3, and e to the minus 2 pi I over 3 times I. So these are the 3 elements. The center of the SU3 consists of these 3 elements, and this in fact is nothing else but Z3. Right? Because if you take this, suppose I call this as omega, I mean some element omega, this omega, let me call it G, some element G. Then G, this is G square, right? Square of this becomes e to the 4 pi I over 3, which is the same as e to the minus 2 pi I over 3, right? So this is a Z3 group. So SU3, the center of SU3 is Z3. In general, I mean, you can now see what will happen if I take SUN. Okay. Now SUN, what will happen? This will be n by n matrix. So this will be now, there will be n such omegas here, right? So you will get omega to the n equal to 1. So here if I look at omega times identity, n cross n identity, take the determinant of that, it becomes omega to the n, and that is equal to 1. So omega will be nth root of unity. But that gives you Zn. Right? Zn. So that is the classification, center of the group. Zn. All right, so now we want to ask the question, how does this act on our different weights? So I can express this in, so the first step is to express it, just like here, we express it as some exponential of the Cartan generator, right? The sigma 3 was a Cartan generator for the SU2. Now we have H1 and H2. Okay? So we want to express this term, omega. So we want to express this omega times identity as some, so this is 3 by 3 identity, as some e to the power of I theta times some combination of H1 and H2. Okay. I don't know, let's say A plus B, H1, H2. In such a way that I get that. Now, if you look at H1 and H2, H1 was 1, minus 1, 0. This was H1. H2 was 0, 1, minus 1. Diagonal. Everything was 0. So we want to get something which reproduces this result. So there are many ways of doing it. But one way to do it is, for example, take this combination H1 minus H2. So what is H1 minus H2? H1 minus H2 is 1. So if I take minus 1, so minus 2 and 1. Now let's take so if I substitute that here in the fundamental representation, it is going to be e to the power of I theta, e to the power of minus 2 I theta, and e to the I theta, right? So if I now take theta equal to 2 pi by 3, right? After all, this theta should be either plus or minus 2 pi by 3 for the center, no? Omega should be that. So if I take e to the 2 pi by 3, what this becomes, you get here e to the 2 pi I over 3, e to the minus 4 pi I over 3, and e to the 2 pi I over 3. But e to the minus 2 pi I by 3, but e to the minus 4 pi I by 3 is the same as e to the 2 pi I by 3, right? So I can as well write it as plus 2 pi I by 3. Okay. So this becomes simply omega times identity. So this becomes omega times identity, where omega is e to the 2 pi I by 3. E to the 2 pi I by 3. Okay. So we can reproduce then this omega e to the I mean this element which I call G. So this is a G element. Then there is a G square and so on. But G, I can express it in this way. E to the where this theta equal to 2 pi by 3. Okay. So theta has been set to 2 pi by 3. Okay. So now we can immediately see how this element will act on a weight given by that. Right? If I look at it, how this acts on a given state, on a state which is labeled by the weights W1 and W2, this is simply going to act as e to the power of 2 pi. So G acting on, or R of G, appropriate representation, acting on a state which is labeled by W1, W2, will be simply e to the 2 pi I by 3 times W1 minus W2 times the state. Right? Because this we have already diagonal. I mean, this is in the basis where H1 and H2 are already diagonal. So I just have to compute what is its. When H1 acts on this, it picks up W1, and when H2 acts on that, it picks up W2. So that's
Professor, I have a question.
Yeah.
So could you please repeat why did you say that the center of the group can be expressed as the exponential of the H1 and H2? I mean, why did you infer that? I mean, in case of SU2, it's simple to see that. I mean, does it always happen that it always be able to?
That's right. It always, yeah. You can always write, for any SUN, you can write that way, yeah.
I mean, how can we see that?
I mean, of course, you could probably write in a much more complicated way. I mean, there's not a unique expression here, right? I mean, I could have also, instead of e to the I theta sigma 3, here I could have written as e to the I theta, e to the I pi sigma 1. No? Because after all, in general, remember, e to the power of I theta sigma, any sigma, let's say sigma I, sigma A, you remember that we went through this exercise. This was nothing else but cosine theta. So, I mean, actually, this was nothing else but cosine theta times identity.
Yes, mathematically it's okay, but I was just thinking that, I mean, in general, we cannot express any element of the group.
Yeah.
Only using the exponential of the H1 and H2s.
Sure.
I mean,
sure. But we are not talking about any element, right? We are talking about an element which is already diagonal, which is actually proportional to identity.
Okay, I
Yeah.
see. So the point was because H1 and H2 are diagonal, so we expect that if we take the exponential and do the algebra, we'll get something like something proportional to identity.
Yeah. I mean, again, just to complete this, you see, here the general expression is this. What I'm saying is there's not a unique representation like this. I mean, a unique way of writing it. I could write it as any sigma A is any A, 1, 2, 3, anything, right? So this will be I sine theta times sigma A. This, we saw that, right? We obtained this expression by just exponential, just expanding the exponential and regrouping them, and you could find the cosine theta and sine theta terms. So now if theta is pi, this drops out completely, right? And you just get minus, cosine pi is minus 1. So you just get minus identity, right? So this shows that I could have equally well taken it to be sigma 1 or sigma 2, doesn't matter. Except that that is not very convenient if I'm using the weights which are eigenvalues of sigma 3. That's not very convenient, right? So it is better to, then if you want to study the reaction, you have to again change the basis. Instead of diagonalizing sigma 3, you find the eigenvalue of sigma 1. No? But since we are always working with, we have already fixed always sigma 3, and we are considering the eigenvalues of that, it is more convenient to use sigma 3. No? That's the reason. And the same thing here also. So it's not a unique thing, H1 minus H2. I'm sure there are other combinations you can write down involving even off-diagonal terms in the SU3 algebra. No? Just like here, sigma 1 is off-diagonal. No? Sigma 1 is off-diagonal. But nevertheless, when you take the exponential, only the diagonal term survives for theta equal to pi. No? So the same thing can happen, but it's not very convenient, because we are diagonalizing H1 and H2. So there, and since we can write it like this, so that is the most convenient. Yeah. There are other ways of writing it, but that's not very useful. No?
I mean, the point was that we are taking the combination of two commutating operators, H1 and H2.
Yeah. That's why the calculation become very easy. If it was a non-commuting, then even to expand the exponential is quite a lot of work. No? Yeah, it's enough to just give, write it in one way. No? Any other way will be equivalent. By just changing the basis, it will be equivalent. Right. So this is what it is, right? So we can now. So this is the G action on this W1, W2. G being this center element, is that. So now you can see immediately we can classify if W1 minus W2 is a multiple of 3. So 3 times some integer. N belongs to some, n is some integer. Okay. Then this is simply 1. Okay. If W1 minus W2 is 3n plus 1. Okay. So in this case, this face is 1 here. In this case, this face is e to the 2 pi I by 3. Okay. And finally, if W1 minus W2 is 3n plus 1 or minus, plus 2 or minus 1 is the same thing, minus 1, then it is e to the power of minus 2 pi. So you can, so if you think about this W1 and W2, which are integers, and in a two-dimensional space, you can plot them, there will be some kind of a lattice. No? There will be some lattice. Lattices are there, some discrete points. No? So you all know the, right? I mean, lattice, what lattice means, right? So this gives you, when W1 and W2 are arbitrary integers, they will span a two-dimensional lattice in the two-dimensional space. Two-dimensional, which is dual to the Cartan subalgebra. So this will be a two-dimensional lattice, and what we are seeing is that this two-dimensional lattice splits into 3 classes, subject to these conditions. If W1 minus W2 is satisfying that, then it is in this class, otherwise this class or that class. Notice also that if you look at the the weights of all the generators, right? So first of all, the H1, H2, etc., the weights were 0, right? Because this commutes with the H1 itself. So H1, H2 doesn't do anything. What about X alpha 1? X alpha 1, the weight was, this was the W1, W2 eigenvalues in the adjoint representation. Okay. This was 2 minus 1. X, so plus minus alpha 1, plus minus alpha 1 is plus or minus 2 comma minus 1. X plus minus alpha 2 was plus minus minus 1 comma 2, and X plus minus alpha 3 is plus minus 1. Right? These were the roots. These were the roots. Okay? So all of them are in this class. You see, so W1 minus W2, 2 minus minus 1, which is 3, right? Same thing here, minus 1 minus 2, which is minus 3. Okay. And here is 1 minus 1, 0. So they are all in this class. All of these guys are in this class. No? So that means if I started with some weight which is in a given class, okay, then how am I going to get other weights in that representation? Other weights in that representation is given by applying these guys, right? But that's not going to change the class, right? Because suppose I act X plus alpha 1, let's say, or plus or minus alpha 1 on a W1, W2. Okay, what am I going to get? I'm going to get weights which will be the weight, this weight plus that weight, plus the weight of X alpha 1. So it will be W1 plus minus 2 and W2 minus plus 1. Okay. Clearly, if W1, W2 is belong to any given class, this is also going to belong to the same class. Right? Because the difference, what you see is the weight of these x's, X alpha 1 or X alpha 2, etc. And they are satisfying this condition. 300. Is that clear? So, yeah. So this is, so now let's see, so for examples, let's look at the examples. Or the examples we studied. So the one, the three-dimensional representation was 1, 0. The 3 representation was 1, 0. And 3 bar was 0, 1. Okay. And the adjoint representation itself was 1, 1. The highest weight. This was the highest weight. Highest weight. Correct. And then we also studied some of the other examples, 6-dimensional representation, which was 2, 0, and 6 bar, which was 0, 2, and so on. A few other representations we studied. No? Now, in all of these cases, so if you look at the class, so let me call this class as the first class, second class, and third class. So this guy is in this class, the second class here. This is in the third class. This is in the first class. This one is in the third class. This one is in the second class, and so on. Okay, you can keep going just by counting this. Now, is that clear? The logic why it was because of the previous statement I made. You see, here we are looking at just the highest weight. From highest weight, I know by just counting this, evaluating this W1 minus W2, I know where it belongs. Once I give you, so it's 1 minus 0, so that is in this class. Okay. But what I'm saying is that, I mean, this three-dimensional representation is not just that weight. There are other weights also. There are 3 states. No? But those 3 states were obtained by applying the lowering operators. But the lowering operator is not going to change the class. Okay? Because the lowering operator is always in the first class, which means it's 3 times an integer. All these roots, they all satisfy, if you look at the W1 minus W2 of these, then that's always is 3 times some integer. For these guys. Huh? So this is the adjoint representation. The adjoint representation, you see W1 minus W2 is in the 3n. That is for all of them. So when I take any of these highest weights and start applying this lowering operators, right? I'm going to change the value of this W1 minus W2 by something which is 3 times an integer. So that doesn't change the class. Okay. So this is a useful, although this is not included in the lecture notes, and but it's useful to kind of keep it in mind. It's just there's the center of the group, and the weights, the set of weights split into classes. And those classes are determined by the action of the center of the group. So there is a classification. And this also kind of gives you a double check when you take tensor products of various representations, and then you see on the right hand side maybe you made some mistake, and when you try to write it in terms of direct sums of irreducible representations, right? Maybe you make some mistake. So the one way to check is one check. This is not going to say that there is no mistake, but at least one check you can immediately make is if the left hand side, if I take a product of 2 representations, let's say R1 times R2, 2 representations, then here there will be various sums of various representations, right? R1 prime, etc., R2 prime, and so on and so forth. Okay. So let's take an example. Suppose I take 1 0 with 1 0. Right? Is a two fundamental representations. I take the product. Now, this one here picks up a phase under the action of G. It picks up a phase 2 pi I by 3. Right? That is that from here, from this 2 pi I by 3. Okay. So if I take both of them fundamental, this picks up a phase e to the 2 pi I by 3. This picks up a phase e to the 2 pi I by 3. So which means e to the 4 pi I by 3, which is the same as e to the minus 2 pi I by 3. So every term here must be therefore in the second class, a third class. No? So that's one check. I mean, so for example, okay, now we'll check that. We'll now start looking at so we'll look at these products now. And we'll come back to it and see that indeed it works out correctly. It had to work out. I mean, if it doesn't work out, that means you have made a mistake in analyzing. So let's try to do this. Let's look at the simplest possible things first. Then we go on to. Oh. Actually, I'm afraid I'm very short. I mean, now there are only 6 lectures left. I don't know how we'll finish. I think maybe. I don't know, I might need some extra lectures the week after. After that. Okay, we'll see how it goes. Okay, so let's look at, so I look at the 3-dimensional representation. So the weights was 1 0. So the weight was 1 0. And then we applied x minus alpha 1. So we get here minus 1, 1. And then I apply x minus alpha 2, and we get minus 1, so it's 0 and minus 1. Okay? This is a 3-dimensional representation. Now I take the product of this with itself. So I'm taking 3 times 3, 3 plus 3. Okay, this notation is just according to the dimension of the representation. And also if there's no star, if it is a star, then it's a 3 bar representation, right? But I'm taking both of them. Okay, just by looking at it, you immediately see that this tensor product cannot have any singlet. Why? Because when I apply G on this gives you e to the 2 pi I by 3. This gives you e to the 2 pi I by 3. So the total thing should be e to the minus 2 pi I by 3 when I take the product of these 2. Right? But singlet, if it was singlet, it should be 1. right? So whatever may be in the right-hand side, certainly there is no singlet. That we immediately know. And also there cannot be a joint representation here because a joint representation again comes with the first class, which means the G acts as omega, this center of the group acts as 1 on that joint representation. So here, I know, before doing anything, I know there is no singlet and no adjoint representation. Right? So now let's try to see what is there on the right hand side. So I have to just take, so altogether in this, so there are total number of states are what? 3 times 3, right? It's a tensor product, so you have to take the product of dimensions. No? So it's 3 times 3, there are 9 states. So how do we get the 9 states? So we have the first of them and the second one exactly the same, 1, 0, minus 1, 1. So this is the first one, and that is the second one, 1, 0, and 0, minus 1. Okay, so these 9 states will be what? For example, the first one gives you this, second one gives you that. That's one possibility, right? Or I keep the first one the same, second one I take this one, or the second one I take this one. So that way I get 3 states just from here, right? Similarly, I could now have started from here. The first guy, I pick up this state from the first guy, and again there are 3 possibilities here. And then finally, so you get 3 times 3, 9, right? So what are the weights? Weights just add up, right? If I take a state which is consisting of 1, 0 in this one, first one, and the 1, 0 in the second one, the weights are just going to add up. So the weights that you get will be, so if I take, so 1, 0 with 1, 0 will give me a state which will have a weight 2, 0, right? It will give you 2, 0. And similarly, and so we just have to look at all the possibilities. So you get here, when I add these two, I will get 0, 1. When I add these two, I'm going to get 1 minus 1. Okay, so there's that. Now I start from here. When I add to that, that gives you again the same state. So there are 2, multiplicity 2 here, right? Because I mean this with that, or this with that. What am I doing? This with that, and this with that give you the same weight when you add them up. So there are 2 states, and this with that gives me minus 2, 2. Okay, and this with that gives me minus 1, 0. Okay. Now, finally, the last one here. This with that gives me, this with that gives me 1 minus 1. So there is again multiplicity 2 here. This with that gives me minus 1, 0. So multiplicity 2 here. And finally, this with that gives me 0 minus 2. So all the ones where I have not put a number, it's just 1. So let me put here a number 1. So this is what we get. The 9 states are carrying this weight. Now if you look at all of this, certainly 2, 0 is the highest weight. But we know what is 2, 0. The 2, 0 we constructed yesterday. It was a 6-dimensional representation. Right? And how was that 2, 0 appearing? So 2, 0, you started with the 2, 0. So x minus alpha 1 gives you 0, 1. And again, because it's spin 1, so there should be 3. This 2 means spin 1. So there should be 3 guys here, so 2 steps. And you get here minus 2, 2. Right? Okay. Now here, from here, this is a doublet of the second SU2. So I will put here x minus alpha 2. So we get here minus 1, 1. Okay. And from here, this is a this is a spin 1, so triplet. So I have 2 steps here, and this one will give you 0, minus 1. So this one gives you 0, minus 1. And one more step, so I'll get here minus 3. No, this not, something has gone wrong here. No, sorry, this is minus 1, right? 0, minus 1. 0, minus 1. I am applying x minus alpha 2 here. Right? So this 2 goes to that, and that becomes minus 1. Correct? And now I again apply x minus alpha 2. So you get here 0 and minus 2. Right? That's it. With all of them, so there are 6 states here. All of them multiplicity 1. Okay? There was a question of here, I mean, because when you look at this here, with respect to the first SU2, it's a doublet. No, first SU2. There was an issue whether there are 2 ways of arriving there. Okay, so in principle it could have multiplicity 2, but we said it cannot be because the number of multiplicity here must be the same as the multiplicity there, because this is one SU2 representation of the first SU2. But here I know multiplicity is 1, so it has to be multiplicity 1. Okay? So these 2 states are not linearly independent. There is only 1 state. Okay? So everything is multiplicity 1, so you get 6 states. So certainly this representation exists. That's the highest weight. Once you have removed them, what is left over? You see, these 6 states, there is this one here, one copy of this one here, one copy of that one. There is only anyway one state here. And then you have 1 minus 1, so one copy of that. And similarly, one copy of that here, and then 0 minus 2. So from this, once you remove these 6 states, what is left over? Left over is one copy of that, one copy of that, and one copy of that. Right? So once you have removed those 6 states, so that means what we are saying is that this is the same as, first of all, I mean, in this language, let's say 3 times 3 gives you certainly a 6-dimensional representation, right? But still, that doesn't cover, because out of the 9, I have taken into account 6 states, right? There are 3 left over, which are just these 3, one copy of each of them. So the ones which are left over is 0, 1, 1 minus 1, and minus 1, 0. But that was a 3-dimensional representation, but not this one, the complex conjugate of that, right? So this is 3 bar. 3 bar representation. That is, and indeed, you see, now just let's check it. I mean, from the here 3 cross 3. This was each of them had e to the 2 pi I by 3 eigenvalue, right, under the center of the group. Center of the group gave e to the 2 pi I by 3, e to the 2 pi I by 3. So the total, the product is e to the minus 2 pi I by 3. So indeed, you see that it had to be 3 star. It cannot be 3, right? 3 star is exactly the, it is e to the minus 2 pi I by 3. Okay? So this tells you that it had to be 3 star. And also it tells you that 6 has e to the minus 2 pi I by 3. Okay? So 6 bar should have e to the plus 2 pi I by 3. Okay? So this is the one array. So 3 with the 3. And of course, as expected, there is no singlet or no adjoint representation here. Okay, this is the systematic procedure, but of course, as you start taking larger and larger representation, it becomes again a mess. No? But I will just work out some simple, small ways, small representations. No? So we did 3 with 3. What about 3 with 3 bar? Or 3 star? I don't know, I'll just use bar. 3 with 3 bar. Usually one uses the 3 bar. In the literature you will find it is 3 bar, which is the same as complex conjugate representation. Now what happens? You see, now the situation is very different. This is G acts as e to the 2 pi I by 3. The center acts as e to the 2 pi I by 3. Here it acts as e to the minus 2 pi I by 3. Okay? So product is 1. Okay? So this means it can possibly have a joint representation and singlet also. All the possibilities are there. Right? we know a singlet must be there. Why? Because you know that this is a complex conjugate representation, and we had already discussed that once you have a complex conjugate representation, you can construct an invariant, group invariant, right? I mean, when we were discussing SU2, we did that, no? That using complex conjugate representation, you can define an inner product, I mean, invariant combination. Okay? So identity must exist here. Since, I mean, some particular combination of these which gives you an invariant state. Invariant state means singlet. No? So singlet must be there. But okay, let's just check that. So now, again, but before I erase this, is there any question on that part? On that, the first one, I mean, this result. Any question on that? It's the same logic which we applied for the SU2, right?
Yes.
When you take J1 with J2, you start taking the highest possible state weight, take that representation, remove that, look at what is remaining, then look at the highest weight there. It's the same procedure actually, right? Except that it becomes more complicated because now you're in 2 dimensions. So it starts becoming more complicated. But okay. So now let's replace that. So I take 3 with 3 bar. So the weights of 3 bar we already know. So these are the 0, 1, 1 minus 1. No, I think I should draw it like that. Yeah, 0, 0, 1. And then I come here. So this becomes 1 minus 1. And this becomes, so this is x minus alpha 2. X minus alpha 1, and here you get minus 1, 0. Right? These are the 3 states for the 3 bar. So this was 3 and this is 3 bar. Okay. So let's again add all the weights of these states. So if we add all the weights, so if I start adding, so 1, 0 with 0, 1 is 1, 1. And that you see what it is. I mean, this was the highest weight of this representation. This was the highest weight of this representation. Add that up, you again will get a highest weight. I mean, really the highest weight in all of that. And that is exactly the adjoint representation. 1, 1 was the highest weight of the adjoint representation. Okay? So this immediately tells you there's an adjoint representation. But anyway, just for completeness, let's do that. So 1, 1, so this gives you that. And now, let's see. So this with that and that with that. Okay, let's see. This with that gives you 0, 0. This with that gives you 0, 0. And this with that gives you 2 minus 1. So 2 minus 1. Let's see. Okay, that I've covered that. Now look at this one here. Minus 1 with that gives you minus 1, comma 2. Okay. Then this with that gives you minus 2, 1. And finally this with that gives you 0, 0. So there is a multiplicity 2 here. Okay. Finally the last one, this with that gives you again 0, 0. So there is a multiplicity 3 here. So there is 1 plus 1 plus 1. Right? 3 states here. This with that. Then this with this gives you minus 1, minus 1. So it's here. And finally this with that gives you 1 minus 2. And now you can see it's exactly the adjoint representation, except that here there are 3 states. Adjoint representation has only 2. The Cartan subalgebra is 2-dimensional, right? H1 and H2. But now there is one more, and that is the singlet. Because once you have removed, so first of all, the highest weight is that. You remove now that, because I know this is 8. This corresponds to 8, because given the highest weight, it is uniquely determines the irreducible representation. So that is an 8-dimensional representation. So you remove those states, so that means this goes out, this goes out, this goes out, all of this goes out, and 2 of them go out. What is left over is 1. So once you have removed that, then this must be the highest weight state, right? But that's the 1, that's a 0, 0, it's a singlet. So the conclusion is 3, so this was, let me just keep that here. So this is 6 times, the original one was 3 times 3 was 6 plus 3 bar. And now 3 with 3 bar gives 8 plus singlet. This 1-dimensional representation of singlet. And similarly, if you had done 3 bar with 3 bar, you would find that this time you will get 6 bar plus 3. That's the okay, so one can keep doing it. I mean, lots of things. But let us just look at, for example, here, suppose I had taken 3 with 3. So let's take 3 products. I mean, oh, can I put a, could I mean, is it okay? I can erase that. Suppose I take 3 cube of 3. 3-dimensional representation. Suppose I take 3 with 3 with 3. Okay. Now this is interesting because now if I look at the action of the center of the group, each of them gives e to the 2 pi I by 3. Right? So the tensor product, it will come with a 1 because it's a product of these 3. So in principle a singlet could be possible. I mean, this does not guarantee there is a singlet, but at least there are possibilities there. A singlet also can have octet and so on. All these possibilities are there. So let us. So how will I do it? Well, I unnecessarily erased. I unnecessarily erased that 6-dimensional representation because what I could do is I could first write this. This I already know it is 6 plus 3 bar. Okay. Then I take the tensor product of this with 3, which is the same as tensor product of 6 with 3 plus the tensor product of 3 bar with 3. I mean, this is the direct sum, right? So I would take tensor product of this with that, which is this, plus the tensor product of this with that. This is like the distributive law. No? When you take the product and your sum inside. Okay, this we already know. This we have worked out. This is 8 plus 1. 8 plus 1. So suddenly singlet exists. Right? Now one can try to work out what is this. Yeah, so this. So let's see. Unfortunately, I erased that. So 6-dimensional representation. 6-dimensional representation was just a square. I mean, was a 2 0 minus 2 2 and 0 1. And then here you got minus 1 1. And here we get
minus 1 0.
Sorry, is it correct?
Minus 1 0. The last one.
Yeah, last one was 0 minus 1. But there was something in between here which is 0 minus 2. Sorry, 0 minus 2. Minus 2. And here it was 0 and minus 1. Correct. Minus 1 0. Correct. So that was this, right? So now I have to take these 6 states. I have to take the product of this, right? 6 times 3. So 6 times 3. So I have to take there are 18 states. So one can just add up all the weights. So we can make a list. So first of all, you get here 3. 2 plus, this. So there is a 3, 0 state. This is certainly a highest weight state. Why is the highest weight state? Because you see, this one is annihilated by x alpha 1 and x alpha 2. This is also annihilated by x alpha 1 and x alpha 2, right, in this irreducible representation. So when I take the product of these two states, it's also annihilated by both x alpha 1 and x alpha 2. So for sure I know this is the highest weight state. Okay. Okay, we have to work that out. But what are the other states? Now, it becomes a bit of a mess. So you get here 1, 1. Now, maybe, okay. Now this will be a mess. 1, 1. What else? So 1 minus 2, so it's minus 1, 2. Minus 1, 2. 2
minus 1.
Ah, good, good. Somebody says, okay. 2 minus 1, okay.
0, 0.
Sorry?
0,
0,
0.
0.
And minus 2, 1.
Minus 2, 1.
Only the opposite, 1 minus 2. The 1 is on the left.
Sorry?
1 on the left, related on the other side.
1 here.
1, yes, 1 minus 2.
1 minus 2, okay. So this is the, or you're taking into account all of that, right? Or that with everything. Now we have to do that. So minus 1, 1. So basically you have to subtract minus 2 from here and 1, add 1 there, right? To this list. Huh?
We have also minus 2, 1.
Minus 2, 1, okay. Yeah. What else you, yeah. Minus 2, 1.
I think 0, negative 1, and minus 2, 2.
So repeat again. So this was 1. After that?
So 0, negative 1, minus 2. So I think the last one there, 0, negative 1, from 3, and from 6, negative 2.
So tell me what are the numbers then, yeah.
Oh, that's like the one
minus 3,
already, yeah.
minus 3, 3.
Oh, this is minus 1. Hmm?
No, it's 2, minus 2, 1.
Minus 2, 1. That is okay. Then what are the
Minus 3, 3.
minus 3, 3.
And 0, negative 3.
0, negative 3.
Negative 3.
Negative 3, okay, sorry.
One, it's like 1, negative 2. Do we have that? I think we have already.
No, I mean, I think just do systematically, otherwise we can miss something. So if you just start from here, just take this and start adding to all of this, row by row, no? So minus 1, 2, 0. That gives you minus 1, 1, right? I mean, I think better to do systematically, no? Otherwise we may miss something. Minus 1, so if I add to that, it becomes minus 1, 2, right? And minus 3, 3. So that is, so let me just remove that. Yeah, it has to be done systematically, otherwise we'll easily miss something. Then
0,
0,
0.
0.
1, negative 2.
1, negative 2.
And negative 1, negative 1.
Minus 1, minus 1, huh?
Yes.
Okay. So that takes care of that. And finally now just take this one and add the top. So 2 minus 1. Huh?
2 minus 1 is minus 4.
0, 0. Okay. And
1 minus 2. 1 minus 2.
minus 2, 1, right? I mean, I'm just going through this row.
Yes, from the left.
Minus 2, 1. Then here you get 1 minus 2, yeah. And
Minus 1, minus 1.
minus 1, minus 1. That's it, right?
0, minus
Oh,
3.
still there is one more.
0, minus 3.
0, minus 3. The 0 minus 3. This last one. Okay, I didn't see. Okay, so now good. So the 3, 0. We don't know what this 3, 0 representation is. We have not worked it out. No. So this we have to work out. Okay, we need to work it out. But there are 18 states. And there are lots of zeros here, right? There are 2 zeros, 2, 0, 0. Okay, so I think all that is missing here is to write down, where shall I write down? To construct all the 3, 0 representation, the 3, 0 representation. So we have 3, 0. Okay, so first thing we notice is that this has, this is, what is it, spin 3 half. So, right, this is spin 3 half representation with respect to first SU2. So there should be 4 states here in this, right, which means 3 steps. So I apply minus alpha 1, I get here 1, 1, again minus x minus alpha 1. So we get minus 1, 2, and then we get here 1 more. So it's minus 3 and 3, right? So that's that. But now these guys are, this is a doublet of the second SU2. So therefore you have x minus alpha 2, so it's minus 1 and 2, that state. Okay, this is a 3, this is a spin 1. So there will be a 0, 0, and there will be a state which will be minus 2, 1. Okay. And this is again a triplet, spin 3 half, so which means 4-dimensional representation. So I'll get here 1, minus 2, and minus 1, minus 1, and then I'll get minus 3 and 0. Okay. That's it. That's it. Okay. Now this is, in fact, one can compute here, one can check. Okay, we know the multiplicities. This is 1, 1, 1, 1. Okay, because there is only one way to reach here, right? But here again, there is only one way to reach. So 1. So this better be 1 also. And but here it is not. I mean, here it looks like there are 2 ways of reaching it. But if you compute it, if you look at this 2 ways, you find that actually there's only one. There are 2 states that are linearly dependent. Okay. So finally, it will turn out to be 1. And then, okay, if this is of course again, these 2 has to be the same multiplicity. And here this is 1, that is 1. So then this also has to be all 1, 1, right? Because this is one SU2 representation. Right? So this is 10-dimensional representation. So once you remove this, these states, so we have 3, 0. So let me remove this 3, 0, 1, 1. So this is removed. Minus 1, 2. This is removed. Negative 3, 3 this is removed. 2 minus 1 is removed here. 0, 0. So 1, 0, 0 is removed here. And then you have minus 2, 1, minus 2, 1. So this is removed. Which one? This one? Which one? Which one, sorry?
Oh, it's negative 1, sir.
Negative 1 minus 2.
No, we removed that.
No, I don't think I removed that, no? Because I only went up to that point. Now there is 1 minus 2, and minus 1 minus 1, and 0 minus 3. So let's see how much. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 states I removed. Eh? Now what is left over? You see the leftover, you have, I don't see 1, 1.
Yeah, the first one is 1, 1. The minus 1, 1.
Sorry, what are the things here?
The first row and the first element.
Something is, I think I missed something here. There should be 1, 1 left over. Actually, there should be.
On the top, the left.
Yeah.
The top of the left.
This one was 1, 1, right?
Yes.
Yeah, yeah. Okay. So then you see, now if you look at all the remaining guys, the highest weight, once I have removed this 10-dimensional representation, then the highest weight is 1, 1. Okay? And that is nothing else than a joint representation. And indeed, you can see there is, if you all the states, a joint is this one. There is this is what we call the x alpha. Okay, yeah, x alpha 1, right? This was there. This is the x alpha 2, and this is just the opposite of that. So x minus alpha 2, and then this is the opposite of that. This is the x alpha 3. This is the x minus alpha 3, and what is here, this one. This is the x minus alpha 1, and two 0 zeros, the two kartans. Okay? So this becomes, so what we are saying is that, so the upshot is 6 times 3 is 10 plus 8, a joint representation. Okay? And so the full thing was a 3 times, so 3 times 3 times 3, therefore, gives 6 times 3 plus direct sum 3 bar times 3, and this we said is 10 plus 8, and 3 bar with 3 was again 8 plus 1. So this is the content. So one 10-dimensional representation, 2 adjoint representations, and 1 singlet. And if you add that up, it's 27, of course. I mean, that means we didn't miss. It's very easy to make mistakes, because, yeah. But okay, this works out correct. And again, you see that the center of the group acts as 1 here. Center of group acts as 1 here because it's invariant identity, invariant state. This is the 1-dimensional representation. And these are adjoint representations. We already saw that this center acted as identity here. And the 10-dimensional representation, whose highest weight is 3, 0, it's also clearly, right? I mean, W1 minus W2, the face was e to the 2 pi I by 3 times W1 minus W2. And the 3, 0 is the 3, 0. So this is just again 1. So a 10-dimensional representation is also 1. Okay, so this is how it works. Okay, and so on. But clearly, this procedure is going to be very cumbersome. As you go to higher and higher dimensional representations. Now, what is this watch? Let's see. I want to just because tomorrow I really need to start the general discussion. So can I take, as usual, can I take another half an hour? Because this procedure is, I think, conceptually is clear. The procedure is exactly what we did for SU2, but it becomes very, quickly goes out of hand to start index. But that's the concept. This is the main concept. But now, let me discuss a little bit about this Young tableau. With the Young tableau, with some rules, I'm not going to explain how you get the rules, but there are some rules with which you can very easily construct all the representations. All the things that appear on the right-hand side.
Professor, I had a short question.
Yeah.
So when we are constructing the states from the highest weight states, we found out that there might be some different paths to get to some state, and then we had to check that if both the states are linearly independent or dependent using the commutational relation and so on.
Yeah.
Is there any shortcut way to say that if they will be linearly independent or dependent, or is it the only way to check by doing calculation?
Yeah, okay, this is the way to check, but after that, after some experience, you will get, I think, okay, this is not, I'm not 100% sure, that if one of the things is 0, W1, this is the highest weight, right, W1, W2, then in that, everything is just 1, multiplicity is always 1. Okay? This is certainly true for the ones that we checked so far, right? We checked for 1, 0. 1, 0 was the 3 2, 0 was the 6-dimensional representation, and 3, 0. No. So all of them had this one multiplicity 1. I think, okay, this is something one needs to check. For example, is it true also for 4, 0? One needs to check that. Yeah. But I think this is probably true. Although maybe I should check it and let you know tomorrow whether it is really true. On the other hand, if you have like the situation when we discussed the 2-1 case, in the 2-1 case, which is not, so neither of them is 0. In the 2-1 case, we had the situation that, so there was a 3 here, 3 elements here, then this went there, so this became 4, right? And the next one, 2, 1, so this was probably like that. And this was a 10-dimensional representation. So in such cases, what happens that if you look at look at this periphery, that boundary. Okay, the boundary, all the states must be only 1. Multiplicity can only be 1. Okay. Then, if you look at the inner one, this will have all multiplicity too. Okay. Now, of course, this was 2, 1. So suppose it is. You started with a much bigger number, so that there are lots of other terms. I mean, there are several. I mean, you look at the next boundary, then you look at the next boundary, and so on and so forth. Then the multiplicity keeps increasing. So this has 1, this is 2, this is 3. Okay. I think this is a general. There's a general pattern. Okay. But to arrive at that pattern, you need to check a few examples. One example I would suggest is look at the 2, 2. 2, 2 example. 2, 2. This diagram will be, so it will be, so the way, so I'll tell you what, I'll tell you what, already from here, you see, this is spin 1 with respect to first SU2 and second SU2. So there will be three states here, 3 states here. And then, so by the time you reach here, so this will be, for example, this will be -2 and 2 plus 2, 4, right? Is it 4? So I'm going here. So this is 0, 3, and this is 4 minus 2. Okay. So is it 4? Yeah, 4, correct. So it will be, it is spin 2. So you see now, so there will be a here element here, element here, and here there will be this here, this here, this here, and this one here, right? So because this is spin 2, so there should be 5 states here, and so on, and this goes like that. So this picture is very nice. So the picture will be like this here. Huh? So here you have the outer periphery. Then there is a inner one. And then there is this one. This is 0, 0. Okay. So you find the multiplicities of these guys is 2. All this inner periphery. Multiplicity in the outer periphery is 1. The multiplicity here is 2. And here is 3. Multiplicity is 3. So this is the, I think, general pattern. So if one of them is 0, I think that all of them are one-dimensional representation. But I will verify that and I will let you know tomorrow. Here is this happens. You can see that you remember I wrote down the dimension formula. Dimension of the representation was W1 plus W2 plus 2 times W1 plus 1 times W2 plus 1 divided by 2, where this is the highest weight. W1, W2 refers to highest weight. So if you do that 2 plus, so 2, 2. So this is the same as 6 times 3 times 3 divided by 2. So it's 27-dimensional representation. And indeed it works out, right? Because outside there are 12 points, outer, so you get a 12 here. Multiplicity each of them is 1. Inner thing has 6 points, but 6 times 2. and then plus 3. That adds up to 27. Whereas if you look at the 3, 0, and let's apply the dimension formula. Actually, that's one thing we can check. We could have checked. So dimension formula of this is, so again apply this formula. So 3 plus 2, which is 5, times 3 plus 1, 4, and that is simply 1 divided by 2, so it's 10. Right? So that agrees with this, the fact that we said that this has multiplicity 1. So, yeah.
Professor, just a quick question. In which textbook I can find the dimensionality formula that you wrote?
Good question.
Or any reference?
Yeah. I don't know. There is a book. I mean, I have not looked at the book, but there is a book which many people like. And that is a book by Georgia on group theory. The title I don't remember. It's Lie algebra or this group theory. I don't remember what the title was. Georgia.
Group theory for particle physics.
That's right. Group theory of particle physics. Correct. That's many people like it a lot. I'm sure there must be a formula there. Dimension formula. In general, it's a very good book for physicists. I think it goes over all of that. I mean, maybe even the construction of all these irreducible representations from the highest weight, at least for some simple ones, small dimensional ones. So it's a nice book, and it relates also to the physics. You know how this enters in physics. So Georgia is a very good book.
Professor, just one little thing. All the things that we have done so far is because we chose the class for the linear combination H1 minus H2, right? And all this, we can obtain the same class but different conditions for different linear combination of H1 and H2.
Yeah, but I mean, but there's not too much choice. I mean, you could of course have changed H1. Basically, what you want is something, some diagonal. So at the level of Lie algebra, what do we want? We want something which is 1, 1, minus 2. Something like this, no? Or actually what we found was 1, minus 2, 1. That was, I think, what we got. But it doesn't matter where this minus 2 is. At the level of Lie algebra, you see, it has to be, I mean, this is going to be traceless. So if 2 of them are 1, the third guy has to be minus 2. But this is okay if I'm going to exponentiate this to e to the 2 pi I over 3. It doesn't matter because e to the 2 pi I over 3 or e to the minus 4 pi I over 3 is the same. No? So this is okay. This exponentiating this guy, so whether you take this matrix or that matrix, the result is the same. So here, I think we chose here H1 minus H2 was this, but you could have chosen this. This is lambda 8 essentially, apart without this 1 over root 3 factor. This is the lambda. This is root 3 lambda 8, and that you can write it as. How can I write? So H1 was 1, 1, 1 minus 1, and H2 was 1 minus 1 here, right? So I could write it as, H1 plus 2H2, right? H1 plus 2H2. That will again, but I mean, in fact, it's almost obvious because the difference between these two is 3H2. But 3H2 is always, if 2 pi I over 3 times 3H2 is e to the 2 pi I H2. So that is always going to be 1 anyway. So anytime you can have something which is, it has to be traceless, such that when you raise it to e to the 2 pi I over 3, they all become 1, 1, 1. That is all. But it wouldn't change. I mean, it wouldn't change. No matter how you represent the center of the group, the 3 will always be e to the 2 pi I over 3. 3 bar will be always e to the minus 2 pi I over 3. It's irrespective of the choice. Okay, now, okay, so the idea or the Young tableau comes from.
I have one question, sorry. Here in the same pair we have 2 minus 1, the multiplicity, the dimension is, because we have 2 here,
Which one are you,
We have some
where are you, so where are you looking at?
Yes, there.
Here, 2 minus 1.
Why we stop at 0, 0 and we cannot.
Ah, no, here, sorry. Here. Yeah, it's continuous. I just forgot to put the arrow. Here also I forgot to put the arrow here. Yeah. Okay, so what is the main idea here? So let's see. So the way the Young tableau, in fact, Young tableau is based on taking the fundamental representation. Basically, just start with the fundamental representation, and because after all, you see, any representation I can obtain by starting from the fundamental and taking enough number of products. So if you just take the fundamental representation, just the fundamental representation, start taking arbitrary number of products of always 3. You can get any representation. Just like if you take SU2, if you take spin half representation and you take enough number of tensor products, you can get any spin, right? Same. Okay. So you can get all the possible representations starting from here. So you take this. So now this object, I can think of it as a tensor. I write it as a tensor. This is 3-dimensional representation. So there are 3 states here, and I will label them by I. So I goes from 1, 2, 3. So I is 1 for one of the states here, I is 2 for the second state, I is 3 for third state. So there are 3 states here. There are 3 states here. So again I put here J. So all this I, J, etc. So let me write it as I1, I2. If there are n of these products, then up to In. I consider this tensor product. So this tensor product is denoted by this symbol. Okay. T, I1, I2. T is this represents for tensor. Okay. So this is a tensor product. Okay. So we start from that, and now so how will it transform? Okay. At the level of group, I mean, if I have a G action, so G is in the fundamental representation. So let's say, so G is an element of SU3. I mean, this is not just for SU3. You could have done for SU2. In the SU2 case, it will be doublet. No, fundamental representation is doublet, spin half. In the SU2 case, so in that case, I1, I2, etc. will be 1 or 2. So whatever the range is, this will be in that range. If you take SUN, then it will be n-dimensional representation. Fundamental defining representation is an n by n matrix, right? So it will be n-dimensional. In that case, it will be all not 3 but n. Sorry, not this n. I mean, if I take SUN, then this indices will go from 1 to capital N. Each of them. That's the idea. Now, what you want is that, so let's look at an action of the Lie algebra element. So if I look at some action of X, let's say, I want to ask the question how it acts on this. Okay? Now suppose X acts on the fundamental representation, which is simply just on the 3, just on a single 3. How will it act? Well, it will act if I write again this 3 as some, let's say, Vi, where I goes from 1, 2, 3, the 3 states. Okay, I'm just labeling the 3 states. It's a 3-dimensional representation, right? So there are 3 linearly independent states. So this is, I'm labeling them by 1, 2, 3. So V1, V2, V3. So how will it act? It will act as some RF X. This means in the fundamental representation of X, which is again a 3 by 3 matrix. So it will act on this column vector. So it will be like Ij, Vj. Right? This will be a 3 by 3 matrix. This labels the row and column, and that is just the column vector. So it's going to transform like this. This is just the fundamental, the matrix for the fundamental representation. I mean, matrix representation, no? 3 by 3 representation of X. So this is the vector, just with only one index. This is a special case of the tensor where you don't have, I mean, this n equal to 1, this small n equal to 1. So there's only one of them. Now, if I look at this now, this object, the tensor product object, in that case, the Ti1, I2, I3, etc., will transform as Rf x I1, say J1, and then T, let's call it I1 prime, T I1 prime, I2 up to In, okay, and then so basically you have the sum of terms, right, where this acts on the, so all I'm saying is that this will act, I mean, you see this matrix will act on each of these index, right? Because, I mean, you can think of this as just V cross V cross V, and n times, no? You can think of that. And you know that at the Lie algebra level, when you take the tensor product, it acts as, it acts on one of them, but identity on the other, plus, you know, it's a sum of terms, right? You remember that at the level of group, it acts on everything simultaneously. But at the level of the Lie algebra, infinitesimal generator, it's a sum of terms, where each term will be in action on just one component here. No? So it's that. So this sum, I mean, I can write it like that. Ik prime. So here what the notation is that the Ik is replaced by Ik prime. No? Okay. So it will be where I goes from, K goes from 1 to n. No? Is that simple? I mean, so this is just saying that this is acting on the kth index, because it's going to be a sum of terms where each time the action will be on the first index or the second index or the third, not simultaneously. No, it's going to be, so this kth term is the one where it is acting on the Ik index. So you get Ik prime, and summed over. Of course, these repeated indices are summed over. I prime k is summed over. So this is the way it is. So let's just yeah.
Professor,
yeah.
So X is an element of Lie algebra, right?
Which one? X is an element of Lie algebra. Yeah. X in the Lie algebra, correct. X is the Lie infinitesimal, so Lie algebra. Yeah, I mean the notation, always the capital X, capital Y, etc. will be always representing the Lie algebra elements. And when I want to write the group element, I will use the symbol G. You know, G is G or H or you know, small letters G. So the group elements will be, I will always write as G or H, etc. This will belong to the group. Yeah. And when I use capital X or etc. I will use that. Okay. Oh, we are getting to, I think I cannot complete it. But let me just do one little thing and then I will continue tomorrow. Now the point is that one can immediately see that there is some nice property. So just to simplify the notation, I will just, let me take n equal to 2. N equal to 2, but you can do it for anything. Yeah? Right? So that it's easier to write. I mean, all this notation may be a bit confusing. So let me just take 2, just n equal to 2. So let's say then I just call it I and J. So I have this tensor. Now under the action of x, what I'm going to get, I will get two terms, Rf of x, Ik, let's say, Tkj, plus Rf of x, Jk, Tki. Right? That's how it will transform. So Tij transforms to Tij under the action of x goes to that, sum of these two terms. Okay. Now let's look at the following. Let's look at the Tji. Suppose I exchange the indices, Ji. And let's ask the question, how is it going to transform? Well, it's going to transform like Rfx, Jk, Tki, right? Because the first index has become J, second index has become I. So I just exchange this I and J. And plus Rfx, Ik, Tkj. No, what did I do? I something wrong here. Kj, sorry, this is Ik. this is ik, and here it is so I exchange ji, so this is ki and that is jk, right? So you see here the j is the first index, I is the second index. So this one is acting on the first index, so this became k, and this, because I mean at the moment I have no idea about, I don't have any particular symmetry in these two indices. No, this is an arbitrary tensor. I don't have any symmetry, so I have to keep track of the position. You cannot exchange the positions. All right, now let us do the following. Let us just take the sum and differences of these two lines. So I want to ask what happens if I take this plus that. Where will that go under the x? So I just have to sum them up, right? So you have, so you see, I take this with that, so I group them in this way, RF, IK, and then you get here TKJ, okay, plus minus TJK. Okay. And similarly, I group these two things together. I mean, I group in the, because this is JK, RFJK, RFJK. No? So I group it like that. RFX, JK. And then I get TIK plus minus TKI. Now you see something plus minus here. Now you see something interesting. If I had taken the plus sign, it will only go to the plus sign here, plus combination. And if I take the minus combination, or on the right hand side again only minus combination will appear. Okay? That means if I define the symmetric part of the T and the antisymmetric part of T, they will, so let me define it like this. This is the standard notation. If you write, define Tij with a small bracket. Okay? This by definition is half Tij plus Tji. Okay? So it's a symmetric part of the this tensor. And the antisymmetric part is this, denoted by that. Tij minus Tj. So you see any tensor any tensor I can write as Tij plus Tij. So I can take any tensor which has no particular symmetry property. I can take a symmetric part of it and the antisymmetric part of it. No? Now the important point is that what this equation is saying is that under this transformation from the Lie algebra transformation, the symmetric part goes to only the symmetric part, and antisymmetric part only goes to antisymmetric part. That means that this big tensor, clearly, I mean, if I started from some state which is the symmetric part, it will stay within the symmetric part. Similarly, if something which I start from the antisymmetric part, it will stay within the antisymmetric part. So this big tensor is already reducible into smaller representations, right? The symmetric and antisymmetric representations. Okay. So therefore, this whole thing becomes very closely tied with the permutation. After all, the symmetry is to do with the permutations, right? You permute the indices, and when you permute, whether you get a plus sign or a minus sign. No? So the permutation group plays an important role. Permutation group of, if you have, here there are only two indices. I looked at the second rank tensor. So here it's a question of only permutation you can have permutation group is only the exchange in this case. No? And with respect to exchange, you can either have a plus sign or a minus sign. Symmetric part will be plus sign, antisymmetric part will be negative sign. And they form different, I mean, certainly the bigger representation of the full tensor is reducible into smaller, no? Which is symmetric and antisymmetric. Okay. Okay, this was for two indices, but now suppose I take I, J, K, whatever, I mean, several indices, then I can do the same thing. You see, this discussion didn't matter I could have just, let's say I put here I1, I2 up to, let's say IK, IL, all the way up to IN. Say K plus 1, for example. And then you can repeat the analysis, and you can again take the symmetric combination of these two or anti-symmetric combination of these two. And they will not mix with each other. I mean, symmetric will not mix with that under the transformation. Symmetric will stay in the symmetric after the transformation. Okay? So this tells you that, okay, so this was just exchange of the two, right? But if this was arbitrary pair, I could have chosen I1 and say IK. I can look at the symmetric part or anti-symmetric part. That will again be, that will not mix, symmetric part will not mix with anti-symmetric part. Okay. Now, so that was just exchange of a pair, but that pair could be any pair. No? And you know that the permutation group of, if there are, here now there are n elements. No? So these n elements, the symmetry, the permutation group is what is called Sn. Sn permutation group. No? If I have n elements here, I1, I2, In, I can consider all possible permutations, and that is what is the permutation group of n elements. And that group is generated by just the exchanges. You can generate the entire Sn by pairwise exchanges. Repeated applications of this pairwise exchanges, you can get any element of Sn. So, okay, maybe I should stop now because now it's already 6. So let me just say that, so this is the main idea behind the Young tableau. Young tableau basically, and the reason why I do not want to go into this too much detail is because to really understand Young tableau, you need to understand the permutation group, representations of permutation group. And that's way beyond the scope of this course. It will just take you completely away from that. So what I will do is, and tomorrow in the first half an hour, I will just summarize what are the rules. You know, there are a set of rules. Unless you understand the permutation group, representation of the permutation group is difficult to really understand that. So what it will be is like some recipes. So I will tell you the recipes and I will some explanations. I mean, trying to make it look plausible, let's say, what the statements are. But that's what it is. But it makes the life much simpler than what we were doing before. It is what we were doing was conceptually completely correct, no? And conceptually clear. What are the steps, no? But in practice, it's very difficult to do. That's the point. Okay, so I'll stop now, and tomorrow I continue with the Young tableau. I'm afraid I'll require a couple of lectures more. I think. So I have to check with Patricia to see.
Sure, we can do this, but I think on Tuesdays and Thursdays we could start earlier because we don't have a class before that.
Yeah, that is a possibility. But the problem is that I have responsibilities at home now. I have to pick up my daughter from the school and give her food and things like that. So that is the problem. Okay, so let's see. So any questions from here?
Professor, I'm sorry, the internet connection dropped in between.
No, that.
So I have a.
I mean, that's exactly the point. You should ask any time. Yeah.
Yes. So I have a question. So here we have done all the calculation in Lie algebra picture. The X is an element of Lie algebra, and we took like the symmetric and anti-symmetric part of the Lie algebra element in the corresponding representation. I was just asking that if we look at it from a Lie group picture, I mean, if we think about how these Lie groups work on, I mean, if we consider the symmetric tensor Tij or the anti-symmetric part, how does it look like from a Lie group point of view?
Yeah, no, that is not immediately. But the point is that this Lie group elements can be expressed as exponentiation of the Lie algebra elements, no? So you can exponentiate them and then yeah. But of course it becomes much more complicated because then at the level of Lie group you have to also, I mean, so exactly what you are saying. So if I take one of these generators, let's say, and exponentiate it with the I, let's say, I put e to the I epsilon x, I will get 1 plus I epsilon x plus I epsilon x square and so epsilon square x square by 2 and so on, right? So now when I go to the representation, Okay, identity is identity. So in that representation, this is just identity plus I epsilon Rx, or a fundamental representation. So, and then you will get epsilon square Rf x square, right? And so on. Now, of course, when you took Rfx, single Rfx, it was acting on individual terms, no? But when I look at the second Rf square, okay, then there will be quadratic terms. I mean, you can have, so you have to apply one more Rf on that, no? So it becomes much more complicated. But nevertheless, since each of this epsilon x, I mean, if I take the symmetric combination, I mean, say this is acting on the symmetric combination, each of the Rfx, when it acts on the symmetric combination, it gives you back against symmetric combination, right? So even if I apply Rfx square, it will still keep you again in the symmetric combination or anti-symmetric combination. So any powers will keep the same, keep it within the same representation, same symmetry properties, no? So therefore the group will also act correctly.
And if we take the exponential of a symmetric matrix, is there any particular property that the exponential will have?
No, the exponential is taken of the generator. What is the symmetric thing is the object on which it is acting.
I see.
Yeah. On those things you don't take exponential. That is the vector space on which it is acting, no? Where the generators are acting. Okay. So then yes, we'll meet tomorrow. I will see if I can try to change Tuesday. You have lectures there. Tuesday and Thursday you don't have the RQM, right? I'll try to see, but then of course I have to check also with the Patricia who is available or not. Okay. Okay. So see you tomorrow.